Welcome back, guys. Let's look into an important concept in chemical kinetics, a molecularity versus order. To know molecularity in order, we need to establish certain terms: intermediate and transition state, elementary step and stepwise reactions. An intermediate is nothing but a species that is formed from the reactants and they can go on to give you the product. So, it is not all that simple when as you write your chemical equations reacting using the product. Most of the time they go through what is called an intermediate. The intermediate is extremely short lived and very hard to isolate. There have been very few intermediates which have been isolated for very few nanoseconds. Example here, triphenyl methyl carbocation, extremely stable intermediate because of your resonating structures, but otherwise intermediate is extremely short lived. A transition state on the other hand is not an intermediate, it is actually a species or an orientation along a reaction coordinate. That is more a theoretical side of definition. You can also call it an activated complex that is formed, it is extremely high in energy. So, your reactant molecules orient themselves and partially combine, and part of the bonds are formed, part of the bonds are broken, and that is your transition state. It is very high, the highest in potential energy in a given thermodynamic diagram, and once the transition state is formed from the reactant, it can go on to give you the product or it can go on to give you the intermediate, and the intermediate can go on to give you another transition state and the final product. So, every time you form a product or an intermediate, you have to go through a transition state. It is the state with the highest energy possible and it is extremely unstable, it cannot be isolated. And a transition state is usually denoted by the symbol double dagger and within a square bracket showing that it is not stable. Now, types of reactions, there are two types for you. One is an elementary reaction and the other one is a stepwise reaction. The elementary reaction, just like our elementary school, it is extremely basic. An elementary reaction is a reaction in which reactant molecules combine together to give you a product without any intermediate. So, it is a single step reaction, it is an elementary reaction. A stepwise reaction is where reactant do not give you products, it goes through intermediate or intermediates. So, it is a multiple step process. Each step might give you an intermediate and the intermediate get consumed to give you the next intermediate and so on and so forth. Finally, it gives you the product. Many times what you see as an elementary reaction is not necessarily an elementary reaction, but it is in disguise. It is actually a stepwise reaction given together. Now that we know the basis of what is an elementary reaction, stepwise reaction, intermediate and transition state, we can actually go into molecularity and order. Molecularity is nothing but the number of reactant molecules combining to give you the products or an intermediate in a given single step. In an elementary reaction, you do not go through an intermediate. So, the molecularity is pretty much how many reactant molecules are combining to give you the corresponding product. So, it is in a single step. The molecularity is always in a single step. Now, for example, let us look at these reactions and identify the molecularity in each of them. So, as I said, the molecularity of a reaction is the number of reactant molecules taking part in a single step reaction. So, again single step is the keyword here, keywords. Our first example is dissociation of PCl5 to PCl3 and Cl2. There is only one reactant molecule combining, so it is a unimolecular reaction. The next is dissociation of HI into H2 and I2. There are two reactants combining two molecules of HI, so it is a bimolecular reaction. The third one is extremely simple, oxidation of sulfur dioxide to give you sulfur trioxide. Two molecules of sulfur dioxide and one molecule of oxygen combine, so it is a trimolecular reaction. Basically, it is a minimum number of reacting particles that come together or collide to give you the corresponding product, and the product need not be a stable product, it can be an intermediate as well. If it's an elementary reaction, there's only one step, so the molecularity is going to be the number of reacting particles combining to give you the final product itself. Couple of things that you want to know about molecularity is, it is a theoretical concept, and the molecularity cannot be 0, negative, fractional, infinity or imaginary, meaning basically it is only a positive integer. Obviously, if you look at these reactions, you see that you cannot have half the molecules combining. We may put half for our convenience sake. For example, oxidations, we can put half O2 on all those. But in a balanced chemical reaction, when you use whole numbers, that becomes the molecularity. So it cannot be negative, fraction, infinite or imaginary. Molecularity generally cannot be greater than 3, because more than 3 molecules may not mutually collide with each other. That's why I stopped my examples with trimolecular reactions. There are chemical reactions where the molecularity appears to be more than 3 from stoichiometric equation. For example, oxidation of HBr. If you look at the equation, it looks like 4 molecules of HBr combining with 1 molecule of O2 giving you a molecularity of 5. So it seems so. But when you actually look into the reaction steps, it's not an elementary reaction, it's a classic example of stepwise reaction. So there are 3 steps involved. Again, you cannot know these steps, somebody has to experimentally determine. When you look at these steps, each step has its own molecularity. Our first step has 1 molecule of HBr and 1 O2. So molecularity of the first step is 2. Molecularity of the second step is also 2. Molecularity of the third step, it's 2. Even though we multiply it by 2, we just need 1 HOBr combining with 1 HBr to give you H2O and Br2. We multiply it so that we get the final tally to get the final balanced equation. That multiplication does not give you the molecularity as 4 for the third step, it's still 2. So that tells you one thing. If you want to figure out molecularity of a given reaction, the reaction has to be balanced in such a way that it's all whole numbers and the smallest, because the definition of molecularity is the minimum number of reacting particles. So we cannot make it 2 HOBr plus 2 HBr. It has to be 1 HOBr plus 1 HBr. So that's your molecularity. This is a basic definition of molecularity. The examples that I have given you are more than enough. Now molecularity, again, it's a theoretical concept. You cannot determine which is your intermediate or transition state by yourself. Somebody has to give it to you. Now moving on to order. Order by definition is the sum of the powers of concentration terms in a given rate expression. Now, how are order and molecularity related? Order is nothing but molecularity of a stepwise reaction, the molecularity of the slowest step. Slowest step is also called the rate determining step. So imagine what happens is, let's say for example, you and your friend has to do a particular task, and one of you is faster, one of you is slower. When are you done with the task? When the slowest person is going to finish his job. So basically the slowest person determines when the job is being done. That's called the rate determining step. All the other steps can be extremely fast. All the other steps, for example, can be done in, let's say, nanoseconds. But there is this one step that is going to take you milliseconds, meaning the overall reaction will be done in milliseconds. So rate determining step is nothing but the slowest step in the sequence of stepwise reaction, and the molecularity of the slowest step is the order. So as we saw in a stepwise reaction, each step will have the molecularity. Let's say that, for example, decomposition of hydrogen peroxide into water and oxygen. Now we just saw that it is 2-step reaction. It's not an elementary reaction, it's a 2-step reaction. The first step involves 1 molecule of H2O2 giving you H2O and O. The second step involves O reacting with H2O2. Now when you look at these reactions, the examiner has to give you it is a rate determining step. Otherwise you cannot decide. It so happens that the first step is the rate determining step. So when you look at the first step, basically one molecule of H2O2 giving you products. I don't care about products, I care only about the reactants. One molecule of reactant giving you products. So the molecularity at the first step is 1. The second step is 2 molecules giving you products. So the molecularity of the second step is 2. But it so happens the first step is the slowest step. Molecularity of the first step is 1. So the order of the reaction is 1. So your rate law is going to be rate equals your rate constant times H2O2 to the power 1. The balanced equation looks like there is 2 molecules of H2O2, but the order is still going to be 1. And a couple of things about order, it's an experimentally determined quantity. You cannot write the reaction steps by yourself. It has to be determined experimentally. Unlike your molecularity, order can be negative, 0, positive, it can be fraction, it can be infinity, it can be anything depending on the slowest step. Couple of things that you want to know. When you know your slowest step, you want to write your rate equation. For example, in our H2O2 example, it's extremely simple. Rate equals K times H2O2. But what if the second equation is your rate determining step? So you cannot write rate equals K into H2O2 times O, because the O is a intermediate. An intermediate cannot come in the rate law. It can be part of a rate determining step, but it cannot come in the rate law. So luckily there is a way to get rid of the intermediate by using the previous step. The best example that we can understand what I just said is by solving a problem that has come in NEET 2016. Now this is what has been given in the problem. A given reaction x2 plus y2 gives you 2xy. As given, if there is a word that says elementary in your question, then automatically the reaction becomes second order, because elementary means it happens in a single step. So it is going to be second order. But here they are giving you the mechanism, proposed mechanism, and they are asking you what is the final order of the reaction. And here all that matters is our slowest step. So now that I have my slowest step, I can write my rate equals some rate constant times what's given on the slowest step. So just a quick refresher, molecularity of the first step is 1, molecularity of the second step is 2, molecularity of the third step is 2. So here I have x, y2 to the power 1 to the power 1. So basically the order is the coefficient in the slowest step. Now this looks like second order, but one of the species that is present here is an intermediate. X is an intermediate. It's not present in the balanced equation. So anything that is not in the equation is an intermediate. So I form an intermediate. And you cannot have an intermediate in the rate law. Because intermediate cannot be isolated, we cannot figure out how it's going to affect the rate. But there is always an equation way that will help you to get rid of the intermediate. In our case, it's our first equation. So from first equation we know equilibrium constant K equilibrium equals, so K product over reactance. So we have x squared over or x2. Equilibrium does not care whether you write intermediate or not. So from this what we can write is x squared equals K equilibrium times concentration of x2, or x equals square root of K equilibrium times x2. Now that we have here, we can substitute for x in our rate equation. So we have rate equals some rate constant times, we have our x times y2. Now I am going to substitute for my x, K into square root of K equilibrium, square root of x2 times y2. Now that I have this, I can sum this up. Rate equals a constant times another constant is a new constant, let's call it K prime, x2 to the power half y2. So that tells you order is half plus 1, that is 1.5. Okay, this is how you get the order of reaction when there is an intermediate present. If the intermediate is not present, extremely simple. For example, if this is given as the slowest step, order of the reaction will be molecularity. Molecularity is 1, order is straightforward 1. And there are no intermediates on the left side, whereas here I have an intermediate, so I have to do. This is harder because there are 2 intermediates and Y forms in this step and it's not an equilibrium step, so they can't give you this. So this is how you get an idea about getting an order from a given sequence of steps. One method to calculate order is through initial rate method, where you can look into few reactants giving you products. What we can do is we can calculate the initial rate of a reaction with regard to each of the reactant. For example, let's say there is 2 reactants A and B. What I can do is I can do 2 different experiments where I can keep my concentration of A the same, change concentration of B alone. So the result that we get, the rate of the reaction, if we monitor that and if there is any change, accordingly we can decide that the change is only because of change in B, because we kept A as constant. Similarly, in another set of experiment, I can keep my B as constant and see the rate, change in rate with respect to change in concentration of A. For example, let's look into a NEET previous year question which came in 2010. Now your key is to see 2 set of reactions. You can pick any 2 that you want, where concentration of either A or B is the same. For example, I would pick 1 and 4. My concentration of B is the same. Now if your concentration of B is the same, then concentration of A is changed, which is made 4 times. Then what happens to the reaction rate, initial reaction rate? Now it is easier if you write the initial reaction rates differently. I have made the concentration of A 4 times, the initial reaction rate has become 4 times. So it's a linear increase. So the order with respect to A is 1. Now what I can do is I can take reactions 2 and 3. Concentration of A is same, but concentration of B is doubled, 0.2 to 0.4. So any change in reaction rate must be only because of B. Now it is always easier if you rearrange this equations, the initial reaction rate in the same 10 power, that way it's easier to compare. If you see, when I double the concentration of B, the reaction rate becomes 4 times, basically 2 power 2 times. So doubling B makes it, the reaction go 2 power 2 times faster. So the order with respect to B is 2. So hence the correct option would be delta, where the order with respect to A is 1 and B is 2. If they ask you total order, that would be 1 plus 2 is 3. Let's look at a different pattern which relates to the same. A question came in 2012 NEET exam. In a reaction, A plus B gives you product. The rate is doubled when concentration of B is doubled, and the rate increases by a factor of 8 when both the concentrations are doubled. The rate law for the reaction can be written as, and they are giving you 4 options. Let's solve this. So what they have said is, let's write the rate law. Rate equals K A to the power X B to the power Y. I do not know what is X, what is Y. We are going to figure it out. So in our first equation, so this is our actual rate. Let's say in our first change, we double the concentration of B. So what we have done is A power X 2B to the power Y. What has become is the rate has doubled. So rate 1 is 2 times the actual initial rate, 2 times the rate. Maybe we can make this 1, the first set changes 2. So rate 2 has become 2 times rate 1. So 2 times rate 1 is nothing but K A power X. So I am going to make it AB to the power Y. It will be A power Y times B power Y. So I am going to do 2B to the power Y is B power Y 2 power Y. Right. Now this is nothing but k a to the power x b to the power y. This is nothing but rate 1. So what I have is 2 times rate 1 equals 2 to the power y times 2 to the power y times rate 1. So 2 power 1 equals 2 power y, so y equals 1. So order with respect to b is 1. So we got that. The next set of experiment they say rate 3 equals k. I am doubling the concentration of A to the power x and doubling the concentration of B to the power y. So now they have said that when you double both the concentration of A and concentration of B, the rate has become 8-fold, meaning 8 times the initial rate. So 2 times rate 1, sorry, not 2 times, it's second set. This is 8 times rate of this one equals k a to the power x times 2 to the power x. This is also double, so 2b to the power y, just like here, we are going to have b to the power y, 2 to the power y. That equals, this is again our rate 1, 2 power x times 2 power y is 2 power x plus y times rate 1 equals rate 1, 8 is nothing but 2 power 3. That tells you 3 equals x plus y is already 1, so x is 2. So that tells you the correct rate expression for us would be rate equals k a to the power x, x is 2, b to the power 1. So that would be the actual expression. This is how you do a problem. There has been many years that you can see the pattern has come. Couple of things that you want to make it familiar is what happens when you increase the rate or decrease the rate by changing the rate constant, or what happens when you change the concentration of A or change the concentration of B. So based on the calculations that we have done, we know that this should be the correct option. X was 2, y was 1. So the total order is 3, rate with respect to A is 2, B is 1. Now there is other pattern that you can get from here. Now what happens when I change the concentration of A, the rate is still the same, what should happen to concentration of B? For example, let's say concentration of A is doubled. What should be the concentration of B so that the rate is unaltered or the same? So now we know that rate equals k a squared b to the power 1. So two different cases, a to the power 2 b to the power 1 equals, the second case would be k, I have doubled my a, so it is going to be 2a. What will happen to b? So let's just say xb, 2 squared. Now the rate has not changed, so this equals this, so my k goes away. So now what has happened is, I can rearrange this side, 2 to the power 2 a times x b, a squared, sorry. So a squared is cancelled, b is cancelled. So what has happened is 1 equals 2 squared x, or x equals 1 by 4. So when you double the concentration of A, you have to decrease the concentration of B by 4 times to compensate for it. You can do the other way around. What happens when you double the concentration of B? So if I double the concentration of B, you can do the same. K A squared B equals K x a to the power squared. I have done 2b. So doing the same setup, you can calculate it. It will come to 1 equals x squared, a squared will cancel, b and b will cancel, there is 2. So x squared is 1 by 2, x is square root of 1 by 2. So you have to change concentration of A accordingly. Now these numbers are not comfortable for you, but it will come. Just know the basic numbers that can happen. What can you do with concentrations in general? You can double or half. You can triple or make it 1/3. So triple means a factor of 27 will come into play. Double means a factor of 4 will come into play. If you get familiarized, then in the exam it is going to be much easier.